Weird. Yeah. Oh well. But yeah, thanks to Mel for putting this together and everybody else for coming and watching. This is just such a great conference. And as Kevin alluded to in the intermission, I've been talking about this at this conference since at least 2009. So this is joint work with Brandon Hansen and Ollie Roche-Newton, and I should say it's really work that I did well over a decade ago, and caused me to bring this up in the problem session every year for, I don't know, 15 years or something like that. And then Brandon and Ollie solved one of my conjectures. So I want to talk about that. I want to talk about the motivation for this conjecture, and of course, give you a new open problem. So the basic idea for this talk is I want to convince you that this is an interesting problem for the application that drove me into the problem. I want to convince you that it's an interesting problem for its own sake. And then I want to talk a little bit about both of those things and then let you escape. So first off, I usually use a particular asymptotic notation, but because this is related to this paper that's up on archive, I'm using the notation that Brandon and Ollie chose. So they use this less than for big O, whereas I would normally use the squiggly less than. So if you look at other papers related to this, and then you look at this paper, things might look different. If we have asymptotic equality, they use a single squiggle, whereas I would normally use a double squiggle. And then this symbol, less than or equal to, less than with a squiggle, is used to bury log factors. And again, this is different from my usual notation. So this is less than or equal to asymptotically, and also with some power n to the epsilon. So there's this conjecture due to Erdős, 1946. Any large finite set of points in the plane should determine at least n to the 1 minus epsilon distinct distances for all epsilon positive. I buried a log here, and I realized that it was going the wrong way, hence the handwritten fix. This was proved by Guth and Katz in 2010, and there are all sorts of related problems and very interesting things around this. But I just want to say, n points in the plane, how many distinct distances? The next sort of big motivator is additive combinatorics, which is of course why we're all here. And I want to give you some basic definitions. Probably most people in the room know these. The sum set of A plus B, given two sets A and B in the reals, is just the set of pairwise sums. The product set is the set of pairwise products. And similarly, we can define the difference set and the ratio set. And this, the ratio set was just discussed a couple of minutes ago. These are going to come up in the talk. And so here's my big conjecture. And this is what I wanted to know about. So this was the big motivation, the big thing that Brandon and Ollie sorted out. So given large finite sets, A and G, just sets of real numbers, if I have that G is about the same size as its product set with itself, so that's, we should know this means that G is essentially some sort of geometric progression if this holds. And it's the same size as A producted with itself, whereas we're not relating the size of AA to the size of A at all. But if we have somehow a geometric progression type set G and this other set A, then I claim AA plus 1 times the geometric progression should grow. That is, that this can't be the same size as AA. Another way of interpreting this is that AA plus 1 cannot have maximal multiplicative structure. That is, AA plus 1 cannot be one of these geometric progressions. This conjecture plagued me from 2009 to 2021. So I guess that would be 12 years. And the first things that you would try, any sort of standard techniques like energy methods will prove that this is exactly bigger than or equal to AA to the first power. And any standard techniques you give will exactly prove nothing. Like you write everything down and you get exactly nothing. So this came up I came across this because this is maybe a little weird. I came across this while looking at dot products. So I want to talk a little bit about dot products. But before I do that, this is the strong conjecture. So this is a big open problem for me. I got what I wanted out of the weak conjecture. We've got a nice dot product result now. But in particular, I think this is a fun puzzle. If I've got a large finite set of numbers, A, just a subset of the reals, and I have the quantity, I have the quality that AA+1 intersected with some product set of numbers is about the same size as AA, where this product set is the same size as AA, then I claim that one of these two has to be essentially a constant size set. So this is a stronger statement in that the weak conjecture just said, well, AA+1 can't have maximal multiplicative structure. Now I want to say that AA+1 really cannot be represented as any product set. And this is a conjecture, but I have really no idea how to approach it. Somebody might be able to refine the techniques of Brandon and Ollie that I'll mention in a minute, get something, but in particular, what Brandon and Ollie showed is well, you'll see. But so this is essentially AA+1, I claim, cannot be a product set. You can probably show that it cannot be exactly a product set, but I mean, it can't be essentially a product set. So dot products. If I've got 2 points in the plane, so P has coordinates P1, P2, Q has coordinates Q1, Q2, we define their dot product the same way we did in calculus class or physics class, whenever you learn dot product. So it's just P1, Q1 plus P2, Q2. Now, in the flavor of the Erdős distance problem, where we looked at the set of distances, we now want to look at the set of dot products. And this is something that I think Alex Josevich, my advisor, prompted me to study this in like 2008 or 2009. Other people have studied this as well. And we basically say, if we've got a large finite point set, how big should this dot product set be? We're going to assume that the origin is not in any point set we consider because it doesn't really add anything to the discussion. So a few of the constructions that I'll mention sort of degenerate if we have the origin in our point set. So let's just ignore the origin for the moment. The basic idea is in the Erdős distinct distances problem, we had points and circles that we were looking at because distances are constant on circles centered at points, but dot products are constant along lines. Now I'm going to give you a couple of slides detailing precisely who these lines are. This is mainly for if somebody wants to pause and rewatch this, because this is a short talk and I don't want to browbeat us with elementary arithmetic too much. But basically, we can describe the set of points that have a constant dot product to a fixed point P as what I'll call this alpha line, L sub alpha of P. And this is the set of points Q that give me dot product alpha. And it can be described, so if I fix a point P, I look at the line through the origin and P, then L alpha of P is this line perpendicular to that direction, and it holds all the points that have dot product alpha. Maybe for a different dot product beta, this is the line, again, it's perpendicular to this line between the origin and P. Of course, this breaks down if P is the origin, hence we're sort of ignoring the origin. Similarly, we can look at the L alpha line of Q. So the problem of counting dot products comes down to counting incidences of points and lines instead of incidences of points and planes. And I'm sure some of you can guess where this is going. A modest conjecture would be that any large finite set of points in the plane should also have at least n distinct dot products. Maybe I want n to the 1 minus epsilon again. Let's just copy and paste this because I bet I'm going to need it on the next slide. Boop. But the best we knew for many, many years was this n to the 2/3. Look at that. Look at that. See, it was there all along. And this follows by a pretty straightforward Senger-Trotter argument. So I claim that, I hope that there are at least n distinct dot products but I can fairly easily show that there are at least n to the 2/3 distinct dot products. That was, let's see, that was state of the art back in like 2009. And Stefan Steinerberger also wrote on this in higher dimensions. He spoke at CANT maybe 8 or 9 years ago. I can't remember. But it turns out if you work really, really hard, like Brandon, Ollie, and I did, you get this very slight improvement. So n to the 2/3 plus some tiny little fraction. And that's going to be the focus of this talk, is going to be explaining how to get this tiny little fraction. Again, not worried about too much what the tiny little fraction is, but just how we beat the n to the 2/3 barrier. Now, first I want to tell you roughly how we get n to the 2/3, because the proof is very quick. I'm going to call an incidence a pair PL, such that the point P is on the line L. So there's a famous celebrated Senger-Trotter theorem, 1983, I think, which says that if I have a set of n points and m lines, the number of incidences is no more than nm to the 2/3 plus n plus m. So what I do is I want to prove the n to the 2/3 bound. It's not too hard. I'm going to fix some dot product alpha and draw lines of the form L sub alpha of P for every point P in my point set. So I've got n points and n lines. Well, Senger-Trotter gives no more than n to the 4/3 incidences. Each incidence, that's a pair PL, each incidence is a case where the point P is on the line L. That means that point gives dot product alpha with whichever point generated the line. So the fact that there are no more than n to the 4/3 incidences tells me no single dot product can occur more than n to the 4/3 times. By the way, this is sharp. You can use a Senger-Trotter sharpness example to generate a point set that it takes a little bit of work, but you can generate a point set that has a dot product occurring asymptotically n to the 4/3 times. I have a paper on that if anyone has any questions, but it's a fairly straightforward construction. You just pigeonhole this. We have n squared point pairs, and you know that every point pair determines a dot product. So if no dot product can occur more than n to the 4/3 times, then this gives you the claimed estimate. So it's simple pigeonholing with Senger-Trotter gives us n to the 2/3. And that's where we were stuck for many, many years. So what I want to do is I want to sketch for you, without going into too many gory details, my approach to beat n to the 2/3 that I was stumped with for, like I said, about 12 years. And then Brandon and Ollie bravely came to the rescue. So suppose for contradiction that n to the 2/3 is sharp. That is that this bound is sharp. That means there is some set of points that determines asymptotically only n to the 2/3 distinct dot products. Then each of these n to the 2/3 distinct dot products should occur roughly n to the 4/3 times. This is a common thing where we're stacking up. So for a contradiction, we're stacking up something that we think shouldn't happen. So it's difficult, but not impossible, to make a single dot product occur n to the 4/3 times. Now we're going to assume that every dot product occurs n to the 4/3 times. Again, asymptotically. There could be small exceptions. Because P dotted with itself is its magnitude squared, if there are only n to the 2/3 distinct dot products, there can only be n to the 2/3 magnitudes of points. Here I'm using a magnitude of a vector and distance from a point to the origin sort of interchangeably. Moreover, and this is similar to the previous 2/3 sketch, these points should live on n to the 1/3 lines through the origin. This takes a little bit of work. It takes Senger-Trotter. If you don't see this immediately, that's okay. But moreover, we can rotate and scale so that the point 1, 0 is in our set without changing the size of the set of dot products. So we have some point set in the plane. Even though the rotating and scaling might change the actual dot products determined by point pairs, it won't change the size of that set. So here's a rough sketch of what this should look like. Each of these points should live on some number of circles, should live on some number of lines through the origin, and they should also have only so many x coordinates. And there are other sorts of projection type restrictions that I haven't gone into. But if we compute the set of dot products and it is no more than n to the 2/3, then the points must live on a set that can be rotated and scaled into this type of point set. Again, I haven't gone through all the details, but it's already, I think, pretty restrictive that I've got a small set of circles and a small set of lines and another small set of lines, and there are just too many restrictions for this point set to exist. And that's where I got stumped. So if we suppose that n to the 2/3 is sharp, we're going to call the set of slopes of those lines to the origin S. And we're going to say that the x-axis points are a comma 0, where a is some set of real numbers. And I don't know a whole lot about a, but I know that it should be essentially a geometric progression. Because if I have points along the x-axis, I'll just go back here, and I consider just the dot products generated by these points, then I'm just looking at a standard product set. So if I have n to the 2/3 points on this line, and the product set can be no bigger than n to the 2/3, that means, well, that I've got essentially a geometric progression, a generalized geometric progression. Every other point would then have coordinates a comma SA, because it's, it's got an x coordinate a, and then it lives on a line with slope s. So either SA is 0 when the slope is 0, or if the slope is non-zero, then I've got a point coordinates a comma SA. If we compute the dot products formed by points of this this shape, we've got a comma SA dotted with a prime comma s prime a prime, and this dot product set looks like this. We can factor out a prime, and we have exactly the set AA times 1 plus SS. So here, remember, AA is essentially a geometric progression, and now the set of dot products is going to be based on a product set of a geometric progression and 1 plus SS. Now this, I'll point out, this is a little unhelpful because the A here is different from this is actually the 1 plus AA in the talk title. So unfortunately, this got named A in the paper, just how the letters fell. So if I can show that 1 plus SS does not have maximum multiplicative structure, then that means this set should grow. So like I said, the set, the size of the set of dot products is the size, roughly equivalent to this size with these restrictions. And as I said, this being like the size of itself is saying it's basically a geometric progression. That's Feynman theorem. So if n to 2/3 is sharp, that means this 1 plus SS must behave sort of multiplicatively like a geometric progression. That is, it should have maximum multiplicative structure. It should have high multiplicative energy, etc. So the crux of the proof, the big thing that Brandon and Ollie managed to do, was they showed that in some sense 1 plus SS cannot behave like a geometric progression. So in the next 5 minutes, I want to give you a sketch of that proof. Again, very loosely, I'll have it sort of on the screen, but I just want you to see it as a sketch of the proof. And then for those of you who are watching this, later on YouTube, you can pause and look carefully at the slides. But let's suppose A is a finite subset of reals. Then maybe A is the same size as its sum set, or maybe A is the same size as its product set, but they can't both be true. This is sort of the center of the classical sums and products problem. In particular, we can show that AA plus AA should be bigger than A to the 1 plus C for some explicit constant C. And one way of saying this qualitatively without quantifying this constant C is by saying AA plus AA is an expander. Just we're saying that if you take the set A, the set AA plus AA should be somehow much bigger. So what about our set 1 plus SS? Must it expand when we multiply it? So specifically, can this be small? And this is the crux of the dot product problem. And of course, the answer is nope. Brandon and Ollie managed to push through this weak AA+1 conjecture enough to get what we wanted for dot products. And so how do we do this? We're going to use what we call convex sequences. And I remember the first time I heard about convex sequences, it was at CANT. I was very excited. I want to say it was Peter Hagerty that talked about it, but I'm not sure. But I tried to push through convex, results with convexity. I couldn't figure it out. Luckily, Brandon and Ollie could. But we're going to call a sequence convex if the gaps increase, right? So the distance between the difference between two consecutive points is growing as the sequence marches on. So if we have an arithmetic progression, then we get this small doubling. We get that the sum set is roughly the same size as the original set. But an arithmetic progression, much like a line, is not strictly convex. So it turns out that A plus A should expand compared to A if A is convex. And this should not be surprising. And I've got a little proposition for you. I claim that some sets are not convex. That is, if you have a sum set, it cannot be strictly convex. This is a fun little exercise. Ollie and I were talking about this during the last CANT, and that conversation kind of led into this paper. So this is nice. So I want to state a convexity lemma. I'm going to give you a sketch of a proof, but this is in the style of Misha Rudnev, and it's the kind of thing that these people have been studying for a while. So that's Brandon, Ollie, Ruja, Shakan, Shoimoshi, and Semeretti. We have the following result. So I've got a set of real numbers, and f is a strictly convex function. Suppose that h prime is strictly less than h, and they satisfy that their difference is less than the minimum difference between any points, any consecutive elements in the set. Then there exist elements in A such that f of little a plus the set plus f of little a prime plus the set minus f of little a plus a, the original set, has size bigger than a squared. So what is f of little a plus a? Well, little a plus a is I'm shifting the entire set A by this small element, and then I'm taking the image of that under the strictly convex function. The proof basically goes by noticing that these intervals are disjoint, and convexity gives that those intervals are increasing in length once I apply the function f. And I can pack intervals in, and I'm guaranteed that there are many distinct elements here. I know I'm going too quickly, but this is just to give you an idea. I think of this kind of like Shoimoshi's 4/3 argument for sums and products. They're stacking a bunch of elements into separate sets, and by doing so, you can sum this up, and you get that this is bigger than n squared. Again, I know I went too quickly, but this is an idea. You can screenshot it if you want to see it. Of course, the paper's on archive. You can read it carefully. But then essentially there are A and A prime that satisfy this, and they are the minimal positive element of A minus A, and then we have those elements A and A prime that will give us this claimed result. So what? A simple corollary of this, if you apply that to the function A is the log of some set, and f of your convex function is e to the t plus 1, then you get this result directly. It's a direct corollary. I know I've got to finish, so I'll just say by doing flashier things, we get a bigger result. You combine that with, oh my gosh, Pluniki-Ruja. You combine that with Ruja triangle inequality. These results do Tagureyev and Shen, which were later improved by Sophie Stevens and Warren. And you get what we want, which is something like AA+1 cannot have maximal multiplicative structure. And you apply this to the set of slopes, and we see that this must expand under multiplication, and we get the slight, very slight improvement that we want by sort of pushing the contradiction backwards. Okay, sorry for rushing at the end. Thank you so much for your time and patience.